we'll discuss relative motion, an application of vector addition and subtraction. The velocity of person with respect to ground will be the vector sum of So as of now, in the third chapter, we have discussed scalars, vectors, then components of vector, and then how to add and subtract vectors, unit vectors, velocity and acceleration vectors. Now, in this video, we'll discuss relative motion, which will be the last topic in the third chapter. Now, relative motion is simply an application of vector addition and subtraction. Let's try to understand this topic by using this example. So suppose a train is running at 15 meters per second and the person is moving in the train at 1.2 meters per second. Now you are watching all this scenario standing on the ground. Now the question arises, how fast the person is moving relative to you, or in other words we can say how fast the person is moving relative to the ground. So logically the answer would be 1.2 plus 15. So this would be 16.2 meters per second. This would be the speed of person relative to the ground. Now suppose the person is moving with the same speed but in the opposite direction, which you can see in this figure. The direction is reversed. Now what would be the speed of the person relative to you? This would be 15 minus 1.2, so that would be equals to 13.8. So this is the speed of the person relative to you when it just reverses its direction. Now let's try to generalize these results. So let the velocity of the train relative to the ground is VTG, and I'm writing it also. This is velocity of train relative to ground. And let the velocity of the person relative to train is VPT. And I'm writing it also. This is velocity of person relative to train. And finally, the velocity of person relative to the ground is VPG. So the velocity of this person relative to ground will be the vector sum of these two velocities. So we can write that velocity of person with respect to ground, this is equals to velocity of person with respect to train plus the velocity of train with respect to ground. So this would be our generalized result. Now let us try to represent this vector addition graphically. So I'll be taking these two cases to represent this vector addition. Now this velocity is a velocity of person with respect to train, and this velocity is velocity of train with respect to ground. And we need to find this velocity of person with respect to ground. So let me draw the vector. This is the velocity of person with respect to train. This point is P and this is T. Now next we have to add this vector with this velocity vector, which is velocity of train with respect to ground. So this is the vector, the velocity vector of train with respect to ground, and this is G here. Now we have to add these two vectors, so we'll get a new vector, and this vector will represent the velocity of a person with respect to ground. In the similar way, we can add these two vectors. So this would represent velocity of person with respect to train, and this is velocity of train with respect to ground. So first I'll be making this vector velocity of a person with respect to train. So it is in this direction. This is velocity of a person with respect to train. This would be p and this is t here. Now next we have the velocity of train with respect to ground, and it is in the right side. So this would be something like that. This is t here and this is, so velocity of train with respect to ground. Now after adding it, we'll get a new vector, and this vector would represent velocity of a person with respect to ground. Now we have written this equation for one-dimensional motion. Here we have considered either the object is moving to the right or left, but this equation is valid for velocity vector pointing in any direction. Let's understand this with this example. Now suppose this person is climbing a ladder instead of walking on the car's floor. So in this case, the velocity of a person relative to a train will be vertical, and the velocity of train with respect to ground remains horizontal. Now here also we can write that the velocity of person with respect to ground will be the vector sum of velocity of person with respect to train plus the velocity of train with respect to ground. Here also this equation is valid. We can take some values also, like you can take that the speed of a person in vertical direction is 0.24 meter per second. This is speed of person in the vertical direction, and the speed of train in the horizontal direction, we can take it to be 0.68 meter per second. This is speed. Now I'll be writing the vectors for these two things. So the velocity of person with respect to train, this would be equals to, this is in the vertical direction, and the magnitude we have 0.24. So this is 0.24 meter per second y cap. I've just multiplied it with the unit vector to convert it into vector, this speed into vector. Now next we can write that the velocity of train with respect to ground, this would be 0.68 meter per second, and this is along the positive x direction, so x cap. This is the way we convert this scalar into vector. Now we have to add these two vectors to get the result. Simple. So this would be the velocity of the person with respect to ground. This would be equals to this value, we have this, so 0.24 meter per second y cap plus this is this, so 0.68 meter per second x cap. Now generally we write the x component first and the y component last, so we can rewrite this equation as 0.68 meter per second x cap plus 0.24 meter per second y cap. Now to find the magnitude of this velocity of person with respect to ground, we have already discussed earlier how to find the magnitude. So this would be under root the x component squared plus the y component squared. So this is 0.68 and squared plus 0.24 and it's squared. So this value comes out to be as 0.72 meter per second. And we can also find the direction. So the direction theta, this would be equals to tangent inverse the y component over the x component. So y component we have 0.24 and the x component we have 0.68. So this would be equals to 19 degree. And we can also show this vector addition graphically. So this vector shows the velocity of train with respect to ground, and this vector shows the velocity of the person with respect to train, and finally its sum is shown by this vector, which is velocity of person with respect to ground, and this angle is theta, which we have calculated to be 19 degree, and the magnitude of this vector is 0.72 meter per second. So I hope you are clear with this. Now, I don't know you guys have noticed or not. If you see this equation carefully, let me first copy it. Just copying it and pasting it here. Now, if you observe this equation carefully, you'll notice that the subscripts in this equation follows a definite pattern. Let me explain. Now, if you see the subscripts in the left side of this equation, we have PG. And here we have the subscripts PT in the right side, and this is TG. From here we observe that a pair of T is added between P and G, and this pattern is true for any relative motion. Of course, the subscripts might change, but the pattern will not change. Now let's try to generalize this result. We have vector v13. This is velocity vector v13. Now it would be equals to velocity vector v12 plus the velocity vector v23. We have just added this 2 in between 1 and 3. We can also represent this vector addition graphically. So here we have this coordinate system. This is positive y, this is positive x, and this vector is vector v12. Now we'll label the tail of this vector with the first subscript, which is 1. So here this will be 1, and the head of this vector will be labeled as 2. That is the second subscript, so 2. Now next we have vector 2, 3. So let this represent vector 2, 3. And the tail of this vector is already we have written as 2. And the head of this vector will be labeled as 3. So finally, the sum of these two vectors is represented by this vector. This is vector 1, 3. Tail we have here and head we have here. So this is how we all add vectors. And one thing you should keep in mind that subscripts are the key to the relative motion. Now one final concept is left. So suppose we have any vector. Let's name it as VRS. So this is the terminal side, so this will labeled as R, and this is the head, so we'll label it as S. Now one question for all of you: what would happen if we reverse the subscript? That is, we are writing VSR. Then what would happen? Just pause the video and try to think. So reversing the subscript will reverse the velocity vector. So this vector will represent VSR. So this is S here, and this is head, this is R. So from here we can say that VRS is negative of VSR.